Hi everyone, this is Kevin from Planetside Software. In this video, we're going to have fun with vector displacements by creating a terrain full of craters. So let's begin. I like starting with a completely undisplaced planet surface. So I'll disable the 3 nodes in the terrain group responsible for displacing the terrain by selecting them and pressing the D key on my keyboard. Then I like to add a landmark object at the origin and scale it to some value that's appropriate for the task at hand. We'll be making a fairly large crater, so the default value of 200 meters is fine. Now I'll add a crater to the project via the Add Terrain button. And zoom out a bit to see the whole thing. I'll mess around with the crater settings, reducing the rim skirt, increasing the rim height, and decreasing the crater's depth values. Basically, I want to keep the entire crater within an area of 2 kilometers. I can break up the crater rim by adding a displacement shader, such as a fake stone shader or a power fractal shader. I'll play around with these settings as well, trying to find something that's pleasing to the eye and works with the scale of the crater. When I'm happy with the overall rim displacement, I'll repurpose the fractal warp shader node from the default project by moving it below the crater shader in the node list and enabling it. The fractal warp shader moves and warps the shape of the crater, but we can recenter the crater by adding a transform input shader after the fractal warp shader. Sometimes it helps to use the ruler tool to see how far to shift a terrain feature back where you want it. The goal is to have the crater centered near the project's origin. I'm going to render a 32-bit EXR file for the vector displacement data, so I need to convert the displacement data that makes up the crater to vector data that can be rendered as an image. I'll add a displacement to vector shader node to the project and connect it to the last node used to displace the planet's surface, which was the transform input shader. I also want the ability to modify the vector data, just in case a third-party application like Zbrush does not use the same units as Terragen, which is 1 meter per unit. To do this, I'll add 2 more nodes to the project, a constant vector node and a multiply vector node. The constant vector node is used to provide the value by which the multiply vector calculates the incoming data. For this video, I'll enter a value of 0.001 in each of the vector channels. The reason for this is that I'll be rendering an area approximately 2,000 meters wide, but Zbrush prefers a scale of 2 units by 2 units by 2 units. So 2 divided by 2,000 equals 0.001. The final output of these function nodes can now be assigned to a surface shader. I'll add a default shader to the project and drag a connection line from the output of the multiply vector to the input for the luminosity function. The default shader has several parameters that contribute to the final luminosity value. For example, the luminosity value will be multiplied by the values assigned to the luminosity function. So I need to set the luminosity value to 1 in order to preserve the values from the luminosity function. Because I want the surface to only contain luminosity values, I'll set the base color value to 0. And under the specular tab, set the Fresnel reflectivity value to 0, and the index of refraction to 1. Next, I'm going to duplicate the planet by selecting it in the object group and pressing Ctrl D. Then drag it closer to the function nodes I just added and connect it to the output from the default shader. The new planet is now textured using the RGB values from the vector displacement data. With the planet node selected, I'll group it to itself by pressing Ctrl G, then give the new group a descriptive name. This will allow me to easily select the group later on within the render layers. Now I'll add a new camera to the project and position it above the highest features of the terrain and point it down at the ground. I'll change the camera type to orthographic and set its width to the size of the terrain I want to render, in this case 2000 meters. Next, I'll add another renderer to the project and assign the new camera to it. The vector displacement image will be square, so set the image width and height to the same value. The larger the resolution, the more detail that can be captured. I'll create a new render layer and also assign the planet group to the object group 1 setting, making sure its render status is visible, but that cast shadows and other rays is unchecked, and that the render status for all other objects is set to invisible, and their cast shadows and other rays is also unchecked. The vector displacement image does not need atmosphere, shadows, motion blur, or global illumination data, so I'll disable all of those settings. I'll set the micropoly detail to 1.0, and under the Edit Sampling button, set the first sampling level to max samples non-adaptive in order to capture all the detail I can. I'll also set the anti-aliasing just high enough to get a cleanly rendered image without a lot of jagged pixels or noise. Under the GI Settings button, I'll turn off any contributions from global illumination or the GI surface details. By adding a render layer to the default renderer as well, I can switch back and forth between the two renderers in the 3D preview when I click on the Reset button. This time, the render status for the planet group needs to be set to invisible, and all other objects set to visible. Finally, I'll set the output of the vector displacement renderer to wherever I want to save the image. Choose the 32-bit EXR format and press the render button. I'll make 4 more variations of the crater, saving each one as a 32-bit EXR file. I can select the default render node and click on the Reset button to refresh the 3D preview and view the project from the perspective camera. Then it's simply a matter of tweaking the crater's parameters a bit. And changing the seed value of the power fractal shader. Sometimes it's helpful to view the individual shader's preview window while making adjustments. The fractal warp shader can also be subtly tweaked. Just remember to reposition the crater with the transform input shader if the crater gets warped too far away from the origin. I'll save each variation to the crater as its own project file before I render it. That way I can come back to it later if necessary. And also because I'm using Terragen's render output variables, so each rendered image will take on the name of the project. Now I'll load the 5 EXR files into Zbrush as textures, create a vector displacement brush from them, and then paint the surface of a flat plane with craters. First, I'll dock the textures palette to the left side of the application, and then import the EXR files rendered from Terragen. Once they're imported, I'll select the first EXR file and click on the To Mesh button. Then drag out the shape onto the canvas. When I click on the Edit button, the shape becomes a tool, which can then be manipulated or sculpted on in Zbrush. This crater looks a little too deep compared to what I saw in Terragen, so I'll reduce the displacement scale by half and click on the To Mesh button again. That's more like it. I'll repeat this process for the remaining EXR files. I'm simply creating a tool in Zbrush each time I select an EXR file and click the To Mesh button. Once I've done that, I'll select the first tool and then append the remaining 4 tools to it. Now I have a Zbrush tool that's composed of 5 crater subtools. Next I need to select a special type of brush called a Chisel Brush. Any of the default chisel brushes in Zbrush will do. This type of brush embeds the 3D geometry into it. I'll dock the brush palette to the left side of the application as well, and then click on the Create Multi-Alpha Brush button. This creates a new brush with the geometry from the 5 subtools. If I scrub the viewer bar, it will update to show each of the craters. To test out the vector displacement brush, I'll load a sphere 3D shape into the canvas and convert it to something editable by clicking on the Make Polymesh 3D button. Then I'll subdivide the sphere a few times in order to have enough polygons to displace. Now I can select each of the crater's subbrushes and drag them onto the sphere to see how they look. Everything looks great. So now I'll replace the sphere with a flat plane so we can make the crater landscape. Zbrush has some flat plane presets located in the Projects Miscellaneous folder under its lightbox. I'll select one of them, then change the default material back to Matte Cap Red Wax. Now it's just a matter of selecting each crater one at a time and dragging it across the surface. I'll vary the rotation and size of each crater as I do so. It's a good idea to save the tool so that you can come back and edit it later on, as well as saving the brush with all the craters as a new chisel brush. Finally, I'll convert the sculpted mesh back to a texture by clicking on the From Mesh button in the texture palette and exporting it as an EXR file. Now I can apply my ZBrush creation to the planet surface in Terragen. I'll use the Quick Node palette to add a vector displacement node to the project. I can assign the EXR image directly to the node's vector function parameter by right-clicking over the input triangle and selecting Create New Shader, Color Shader, Image Map. I'll choose the Position Center option so that the image map shader positions itself from the center of the image and not the lower left corner. Then I'll set the size values to match the camera's orthographic width values used to render the individual crater images. Under the Color tab, I'll check the Data is Linear checkbox because the EXR data is already in linear color space. Now I just need to connect the output from the vector displacement node to the node following all the displacements, which in this case is the Compute Terrain node. Terragen will ignore the previous displacements and get all the displacement information from the vector displacement shader. At first glance, all the terrain displacements disappear, but this is because we need to reverse the effect of the multiply vector node that we added in order for our rendered vector displacement image to fit in Zbrush. This time, we'll divide the area that the image map covers, 2,000 meters, by Zbrush's preferred unit value, which was 2, to get a value of 1,000. And there's all the sculpted craters applied to the surface of the planet. If I want even more craters on the planet's surface, all I need to do is replicate the vector shader by using a shader array node. I'll add one to the project and connect the output of the vector displacement to the shader input of the shader array. Then connect the shader array to the Compute Terrain node. The shader array node duplicates the shader assigned to it in a grid-like pattern based on the number of rows and columns you tell it, and the space between them. By default, only the shader instances along the four corners are displayed in the 3D preview. However, you can enable the Preview All Instances button to see everything. In order to break up the grid-like pattern, I'll copy and paste the three nodes. This time, I'll reduce the area covered by the image map by half in order to make smaller craters, and connect the output of the first shader array node to the main input of the second shader array node. Then connect the second shader array node to the Compute Terrain node. I'll change the rotation parameter of the second shader array node to something different, like 45 degrees, and then select the second shader array node in the 3D preview and translate it into a different position. Now the two shader array nodes are overlapping and the repeating pattern is not so visible. I'll render a test frame to see how it looks. Then I'll make any final adjustments and render a full frame. As you can see, taking advantage of Terragen's vector displacement workflow can open up an infinite number of possibilities. You can easily create overhanging structures or sculpt specific details in a third-party application like Zbrush. And generally speaking, a vector displacement workflow will render faster than a standard displacement workflow because all the displacements are built into the vector displacement image. I hope you've enjoyed this video and learned something new. Be sure to subscribe to the Planetside Software channel for more video tutorials and content.